Yeah, so there were a couple of questions yesterday participant asked and I could not answer in that time. So maybe we can answer those quickly and then move to the next session. Yeah, so the question was like, first question this Monica has asked that can we use this other basis, sorry, what do you call, VV or HV also can we use? So the answer is yes. In a well state, we can have anti-correlation and correlation as well. So 1 by and 0 1 H V plus V H, and that is equal to 1 by square root of 2 0 1 plus 1 0. So in that case, the relation is basically the correlation is anti-correlation, means if one of the person measure his or her photon, like this is P1 and this is P2, P1 and P2. So before measuring any photon, they do not know whether they will get horizontal or vertical. But if one of them measure first, then they see like this. If some of them is measured horizontal, that first photon is measured to be horizontal, then they instantly know that the other person, maybe far away, will have vertical polarization on measurement, and vice versa also. If one of them measures first, then let's suppose P2 measure first, this P2 photon is measured to be horizontal, then instantaneously this person who is measuring P2 knows that the other photon P1 will be measured in vertical polarization. So yes, this kind of entanglement is also possible, and the correlation can be anti-correlation also. So another question was asked that can we entangle be extended to more than 3 qubits? So yes. So yesterday we have seen for this 3 qubit entanglement in ZH state, wherein the entanglement was like this: 000 plus 111. And for this we have seen the circuit like this, in which first qubit is applied Hadamard gate, and then we apply a control node from first to second qubit, and another control node from second to third qubit, that gives us this state Z at Z, and just 4, and we put a like this, then it will be a 4 qubit entanglement, in which the state will be like this: 4 times 0 plus 4 times 1. So in that case, these 4 qubits will be entangled, and before any measurement, they do not know whether these 4 qubits will be zeros or 4 qubits will be 1. But once one of them measures 0, then automatically other will be fixed to be measured to be 0. So the answer is yes, and we can generalize this Z at Z state, and we can increase it for 4, 5, and 7 qubit also. So what exactly is qubit and basis? So this second two questions I will answer with block sphere. So see just now. So can we think of this basis as a quadrant in Cartesian? Yes, and we can denote this kind of state, and we can visually view on a block sphere that I will explain in a couple of minutes. So Beta asked this question: how to remove the error? So it was the question when I explained that we can create Bell states on a quantum computer, and which we have seen the result. But we also get couple of 0 1 and 1 0 also, some states on measurement. So most we get this only, but couple of time we get this non-desired states 1 0 0 1 0 1 and 1. So I told that this is because of error in the QPU of quantum computer, and there are different kinds of errors. So some errors are called measurement errors. So while we measure the qubits, sometime error is there. While we initialize the qubit, there are some errors, and these qubits are very fragile, and there this entanglement and the superposition cannot be held for longer duration. So within microsecond, they come to the ground state 0. So there are several kinds of error, and to remove those errors, in quantum computer, we have this quantum error correction codes. So we just need additional qubits for redundancy, and some quantum error correction codes are there. So using those, we can implement and remove these errors up to certain extent. So generally nowadays, so computers, QPUs with hundreds of qubits, physical qubits, we call them as a hundreds of physical qubits. Using those 100 physical qubits, we can have 10 to 1 logical qubit. 10 to 1 logical qubit. Logical means the perfect qubits which will exhibit this entanglement and other phenomena for longer duration without any error. So you see that at least 10 to 100 qubits we require for physical to logical. Why? Because the qubit lifetime is in microseconds. So we want to increase that lifetime. So for that, we do some kind of error correction codes with redundancy and try to improve the lifetime of a qubit. So this is one obstacle or engineering challenge, that to have one logical qubit, we require 10 to 100 physical qubits. So that's why we do not have a quantum computer which is large enough to break current crypto schemes, because they require thousands of logical qubits. So currently we do not have those much logical qubits. And there is one another technique called quantum error mitigation techniques. So in error mitigation, what we do is we observe the results and we do some processing to mitigate those errors. Okay. Yeah, just a second. Yeah. So let me answer those questions first. Yeah. So to entangle two qubits, we have this Hadamard gates and control node gates. So yes, the answer is yes. So as also explained yesterday, so to entangle two qubits, Q1 and Q2, we require to apply one Hadamard gate on the one qubit and then a control node from first to second qubit. So this C node is applied from first to second qubit. Then we get beta 00 state, and that is nothing but looks like this. Okay. And depending upon this different values of this Q1 and Q2, if we initialize Q1 with 0 and Q2 with 0, then we get this state. But if we initialize with different values of 0, 0, 0, 1, 1, 0, and 1, 1, then we get different Bell states, and we call them 5 plus 5 minus or likewise. So there are 4 possible Bell states, and they exhibit correlation or anti-correlation in their measurement. So one question was by Senthil Kumar. What is this deck? I do not understand. Can Senthil Kumar highlight what is he mean to say? Deck, please. Okay, so the answer, the question remains that to explain those basis and this qubit state using block sphere, I will explain you guys. So just let me open the whiteboard so that I can explain.
There are few more questions posted.
Yeah, so let me see. So I'm starting with the, will there be will be only 0 and 1 state in the quantum system? Can there be 2? Can there be state 2? No, no. So what we are trying to say here is it's a two-level system, means there will be 0 and 1 states. So a qubit can be in superposition of both 0 and 1 simultaneously. Okay. So the answer is only 0 and 1 we are considering, and this two-state system. So what is physical and logical qubits? So what I mean to say is that physically we may have hundreds of qubits in our quantum computer, but those qubits are physical, means there are qubits, they have some properties, but what happening is that they cannot sustain that qubit lifetime. Like qubit lifetime is in microsecond. So if I want to implement some quantum application or some quantum program circuit I want to run, then it should run within the lifetime of that qubit, that is in microseconds only. So if my program is running for, let's suppose, milliseconds, so then I will not get the correct results because of errors in the qubit's behavior in entanglement and superposition. Because those entanglement and superposition behavior persist for microsecond only. So if you want to use the qubit for longer duration for our quantum application, then it will get erroneous. this entanglement and superposition will collapse and it will get corrupt. And there are many other, like we initialize the qubits with zero states. What happens is sometimes it is not initialized with zero. So those kind of different errors are there. Just a second, let me take a call. Sorry. So physical qubits are the qubit which are having, but they are not perfect. Means perfect means when we initialize with zero, it should be initialized with zero only. It should not be like 10,000. It should initialize with one. So those physical qubits are there, and we want logical qubit. Means they are perfect. Their superposition and entanglement will last longer as much as our quantum algorithm is running. So to get physical to logical, we need quantum error corrections. So for that, we need some redundancy. Okay. And for that, the ratio is like 100 is to 1. So 100 physical qubits, physical will give us one logical qubit. So this is general ratio as of now, but the qubit quality is slowly improving. So that will improve in future. So currently we have quantum computers with max is 1000 qubits. So in 1000 qubits, we cannot have more than 10 logical qubits. And to break the ciphers, we require thousands of logical qubits. But that's an engineering challenge. Progress is happening on that, and it will resolve in future. So am I audible now?
Yes, you are audible.
Participants? So okay, so that's a personal issue. Yeah. So I think we have answered those questions, and we can come to this thing, that is block sphere representation. So in that, I will try to explain the basis phenomena also, and then we will be using it for our further session. So the qubits can be mathematically represented using a block sphere, this kind of sphere which I have shown here. And in that sphere, what we are denoting is that it's a unit sphere. Okay, so the radius is a 1. So north is a 0 state and south pole as a 1 state. So these are this Cartesian system, x, y, z axis are there. So z plus z we are denoting as 0 state, and minus z we are denoting as a 1 state. Okay, and what we are saying is that any point on the surface of this unit sphere is a valid single qubit state. Okay, so yesterday we have denoted a qubit by this alpha times 0 plus beta times 1, and the condition was mod alpha square plus mod beta square should be 1. That is nothing but the probability of getting 0 and 1 on measurement, and that sum should be 1. So we can represent this qubit on a block sphere also with this kind of representation. And what we are saying is that this psi is basically our a generic qubit state psi on a unit sphere surface. And how we can write in this with this theta and phi here. So and phi is in psi plane. So what we are doing is we are projecting this psi state on xy plane, and then we are measuring the angle of this projected vector p from plus x-axis. So from plus x-axis, if we measure this angle, these we call as a phase angle phi, and we can rewrite the qubit in this notation where psi is cos theta by 2 0 plus e theta by 2. And if you do this, so in that case, alpha is what? Cos theta by 2, and beta is what? This entire expression ei phi sin theta by 2. And if you do this mod square of this term and you add them, that is nothing but cos square theta plus sin square theta, so that will be 1. So our this probability constant will be also there, and the same thing we can write like this. So instead not writing every time this alpha times 0 plus beta times 1, we can write this qubit state psi like this is a column vector. So what we write in this column vector is this coefficient of 0 as the first value, and then coefficient of 1 as beta. So what we practically use is psi as a alpha and beta as a column vector to denote the state. Now, what is this z plus z, or basically 0 will be here. So 0 we are calling is as this. So it is nothing but 1 0. Why? So this is also equal to this cos theta by 2 is your alpha, and e I phi sin theta by 2 use your beta. So alpha is nothing but cos theta by 2, is nothing but e I phi sin theta by 2. So if you put the values of theta and phi for this point here, so you will see that both are 0. So this becomes 1 0. For in this case, the theta is what? 180 degree. So this will become, so 1 will become 0 1. So, and now what we are seeing is that these two states 0 and 1 are denoted by column vectors 1 0 and 0 1, and these we call as a computational basis state. States needs to be normalized state, means their norm should be 1, and they should be, this basis should be perpendicular to each other. So that should be orthonormal basis should be there. So for orthonormality, we can do is we just do the this thing. So these two states 0 and 1 we are calling as a basis state. So to become a basis state, they should follow these two constraint, that is orthonormality, orthonormal basis, orthonormality. So when we do the this inner product of these two things, so it should be 1, and if you do inner product with other state, then it should be 0. So this is basically normality, and so it is this orthogonality, and this is normality. So this shows that these two vectors 0 and 1 are orthonormal. So now the thing is that using these two vectors, we can write any generic state like this: alpha times 0 plus beta times 1. We do not write this completely alpha times 0 plus beta times 1. We just write it like alpha and beta we write in the column vector form. So these two can be used to denote the state psi, these two coefficients alpha and beta. And if you want to compute the probability of getting 0, then we will do the mod square of alpha, and this mod square of beta will give the probability of getting 1. So basically what we are trying to say is that the psi state, how much it is towards this plus z axis, that will gives us the probability of getting it 0, and how it is close to 1, that will give us probability of getting 1 on measurement. So when this is the same vector, then probability of getting 0 is 1. If this is the vector of our state psi, then the state is 1 only, so it will be measured 1 always. Any point on the equator, this equator or the xy plane, that is equidistant from south pole basically. So all called equal probable states, means there are 50-50 chance that they will be 0 and 1. And these special states are like axis is denoted by, so plus x is nothing but it is 0 plus 1 by root 2. Okay, and similarly this minus state is nothing but the minus x axis is written as 0 minus 1 by root 2. So, and it is denoted as at plus x axis it is the state, and it is at minus x axis. So far what I have explained to you guys is that using the block sphere, we can represent a single qubit state graphically, and the equations like this: alpha is cos theta by 2 and beta is sin theta by 2, and theta and phi are like this: angle with the plus z axis and angle with the projection on xy plane with plus x axis will give us phi, and we can write them as a column matrix. So 0 and 1 are written as like this. So now if a general state is given like this, and the condition is 1. So so the voice is not okay. Participants, the voice is okay or it is breaking in between?
For now, it's fine, but sometimes,
Okay, so
sometimes,
maybe the net. Okay, so maybe the network issue is there. But is it okay now or still breaking?
it's fine now. For now, it's fine.
Okay. Okay. So in between, sir, if there any issue with the audio video, then you can just chat or message me or yeah. So these are the two state which we call as a plus state and minus state, and they are basically on the plus x-axis point and minus axis point. And they are, if you see, they are 0 plus 1 by root 2. Basically, they are superposition of 0 and 1 state both. And here also 0 minus 1 by root 2. So again, if you measure these two state plus and minus 1 on z basis. So z basis is what? This. So what we are trying to say here is, if you want to measure the qubits in z basis, or that is our basically computational basis, then how you measure those states? So for that, what I have done is I've already created some notes for you. So maybe I can rewrite like this. So if you want to measure a state like this, alpha and beta, are you able to see it? So this is your state psi, and you want to measure along z basis. So in z basis, what we have? We have two options. Plus means zero state, and minus means one state. So in z basis, so is my whiteboard visible to everyone?
Yes, it's visible.
Okay, someone written in the chat that it is not visible. So where I'm writing is visible. Okay. So what we are trying to say is when we measure the qubits in Z basis, then what will happen? Either we will get 0 or 1. Basically, it will be towards this state 0 plus or minus 1 is this basically minus Z is basically towards this south pole. So whatever vector is there, suppose this vector is there. So it is how much percentage towards 0 and how much percentage towards 1. So it will give us the probabilities. So how we can compute those probabilities in Z basis? Basically, what we do is we do the inner product with zero state and mod square that thing. That will give us the probability of getting plus means basically zero state or the this side. Same way, if you want to calculate the probability of getting minus state or basically the minus z axis, that will what we'll do is we just do the inner product of the state with one state, and then do the mod square. So just understand here what is the measurement in z axis is you will just do the inner product with 0 and 1 and then do the inner product mod square. That will give you probability of getting plus means 0 state or getting minus means minus z axis means getting 1 probability with this two inner product and their mod square. So how we can calculate this inner products? So just understand this thing that this is the 0 state and this is your psi state, okay, in cat notation. So here if you find that this is bra notation. So how we can write this cat notation into bra? Just convert this, this is basically psi, then its equivalent bra notation will be nothing but a row vector. Uh, so transpose conjugate of this is basically the bra notation. So cat is this, then the bra will be like this, alpha plus and beta plus. So basically transpose conjugate of this psi will give us bra psi. So this is your, this thing is there, and 0 is already, we know it is 1 0. So what you will do is, to get this probability of measuring 0, you will just do the inner product of these two numbers. So it will be what? This is your psi and this is your 0 state. So you just multiply them. It will be alpha mod square. So the probability of getting 0 or the plus z axis on measurement in z basis is mod alpha square. Similarly, if you do it for this states, then what is the probability of measuring minus z axis? Is you do the inner product with one state, and this mod square will give us the probability, and that will turns out to be mod beta square. So we already seeing this thing now, that what is this mod alpha square and mod beta square? Those are probabilities of getting 0 and 1 on measurement in z basis, which we call as a computational basis that we by default use. Suppose if you want to measure in another basis, okay, so there may be several bases, okay. So suppose if you want to measure in another basis, that is called x basis. So if you want to measure in x basis, see here, so just focus. Are you able to see this whatever I am showing?
Yes, we can see.
Yeah. So till now what we are doing is, we are doing in the z basis measurement. Suppose if you want to measure in x basis, so what is your x basis? If you remember, so in x basis there will be two state, plus x axis that we denote as a +1, and minus x axis that will denote by -1. So just we can write their expression. So minus x minus state is there and plus state is there, and those are noted by these two, 0 plus 1 by root 2 and 0 minus 1 by root 2. So these two states we have, and these are also basically orthonormal, so they can constitute a basis, and in that basis also we can measure. So if you want to measure in plus and minus 1 basis, then what you will be doing is, you will be doing the inner product with the plus and minus states of the psi state. So if you want to measure the psi state of a single qubit in plus and minus basis, then what you will be doing is, you will be doing the inner product with plus and minus 1, and then doing the mod square will give you the probability. So if you put these numbers here, just a second. Is it freezed? Just a second. I want to go scroll it down. Yeah. Just a second. Sorry for apologies. Yes. Can I just reopen it? Let me just reopen it. It has. Let me just reopen the whiteboard again. Maybe it has frozen. So basically what we are doing is, we are trying to prepare ourselves for Bell state measurement. That is our topic today. Understand first that how we do the measurement in Z basis, and then how we measure in X basis, and then we will move to Bell state measurement basis. Yeah. So the screen is visible, whiteboard is visible now,
Yes,
participants?
it's visible.
Yeah, perfect. So what I told is that, what we are doing here is, if you want to measure in Z basis, then you will be interpolating with inner product with 0 and 1 state. And if you want to do measurement in x basis, so x basis are plus and minus states. So you will be doing inner product with plus and minus 1 states. And now, so suppose what we are trying to say is that we are doing inner product with plus and minus states. Suppose if you do not have this plus and minus basis states, and still you want to measure in z basis only, but you want the result to be in x basis. So how we can do it? So if you see here, if you measure in plus and minus basis, then what we get is, so we can write those plus and minus in terms of x basis also. So what we see here is that if you measure a state in plus basis, then what you will get is, so just let's do it manually so that we will be able to appreciate that thing. Psi state, and you are measuring in plus basis. So what you will be doing is, psi is nothing but alpha beta in row form. So just write what I did is transpose conjugate. So I get this state, and plus state is what? That is 1 by root 2, 1 by root 2. You remember? Plus state is what? 0 plus 1 by root 2. So if you write in a column vector form, then it will be 1 by root 2, 1 by root 2. Coefficient of 0 and 1 states both are 1 by root 2, 1 by root 2. So you will be doing inner product with this. So what you will get is alpha plus beta by root 2 mod square. So that is the thing we will be getting. Okay. Yeah, plus x axis is plus state, and minus x is minus state. So, and this is nothing but probability of measuring in plus x axis, or we are measuring in plus basis. So this is the thing we get on measurement in plus basis. Okay. Now what we are saying is that if you do not have this thing, what you call, if you do not have this thing, so what you can do is, instead of having this plus basis, if I apply the Hadamard before measurement and measure in z basis. So what we are trying to say here is, can we do the same thing with z basis? So what they are saying is that if we apply the Hadamard gate before the measurement, then it Hadamard plus this z measurement will give us x basis measurement. So why? So if you remember from yesterday thing, so Hadamard of 0 is what? 0 plus 1 by root 2, and Hadamard of 1 is what? 0 minus 1 by root 2, and that is nothing but plus state, and that is nothing but minus state. So if you want to measure in x basis, then what you can do is, you can just apply a Hadamard before the z measurement, and just apply Hadamard and do the measurement in z axis. That will give us x basis measurement. Because of this inequality is so this is in z basis, and we apply the Hadamard, then it becomes plus basis. So see here, this 0 and 1 are from z basis, and we are applying Hadamard, that is giving us plus and minus 1. So what we are trying to say here is, if you just apply a Hadamard before this z measurement, and then the resultant measurement is basically in x basis. Okay, and we can prove it also. So that's not a concern now. So what we are trying to say here is that you can do any measurement using the z basis measurement. So you just need to apply some unitary that converts the z basis into the desired basis. So suppose you want to measure in some basis b prime, or maybe just call it basis b. If you want to measure in basis b, then what you need to do is, you need to apply some operation here, some quantum operation, unitary u, and this unitary u and z, that becomes b. Then if you just apply the unitary before z measurement, then that will give you measurement in b. So the idea here is that you can do all possible measurements using z gate, z measurement only, or the computational measurement only. Just you need to apply some unitary or some quantum gate before z, then it will give you the measurement in desired basis. So we do not measure in every basis. We just do in computational. And if you require measurement in some other basis, we want to transform them, then we just apply some quantum gate which gives us the resultant B. So far what we have seen is that using the Z only, we can do different measurements in different bases. So the talk and the thing which we want to do or establish here is we want to do the Bell basis measurement for the 2-qubit system. So if you remember from yesterday's class, we can have 4 different Bell states, and those are basically 0, 0 plus 1, 1 by root 2 and likewise. And we also explained that they are given names 5 plus, 5 minus, psi plus, psi minus. Okay. And what we are trying to say here is that these 4 states are forming an orthonormal basis. Why? Because when we do the inner product of the state with itself, it gives us 1. And when we do the inner product with other states, then it results into 0. So you can see here also. So how we will do the inner product of this 5 states? So this 5 plus can be written like this. How we can write this 5 plus state? We can write like this. So the states is basically how we write is 0, 0 coefficient we write here, 0, 1 coefficient, 0, 1, 1, 0 and 1, 1. So in 2-qubit system, computational basis are these 4 states, 0, 0, 0, 1, 1, 0 and 1, 1. So instead of writing the state like this, alpha times 0 plus beta times 0, 1 plus gamma times something like this, we do not write the state completely as an expression of this. What we write is their coefficients, alpha, beta, gamma and delta in the column form. So what we do here is alpha, beta, gamma and delta. We write like this. So for our state is 5 plus. How we can write this 5 plus here? 5 plus will look like this. So coefficient of 0, 0 state is what? 1 by root 2. So first parameter is 1 by root 2. Second, 0, 1 is not there. So this beta is 0. And similarly, coefficient of 1, 0 state. So 1, 0 is not present in this state. So that will be again 0. And coefficient of 1, 1 is here, 1, 1 is there. So coefficient is 1 by root 2. So this is the 5 plus state. In computational basis matrix form, we can write like this. Now what we are trying to say here is do the inner product with itself. So inner product with itself will be what? 5 plus inner product with itself, 5 plus. So what we will do is just we write in the raw form. So it will be like this, 0, 0, 1 by root 2. And this side 5 plus is what? Column form. So 1 by root 2, 0, 0, 1 by root 2. Just do the inner product, just do the product. So it is 1 by square root of 2 plus 1 by square root of 2, that is half. And again 1 by square root 2, this 1 by square root 2, that will give you half. So it is giving us 1. So the inner product with itself is 1. And if you do the similarly inner product with other states like 5 with 5 plus with psi plus, then all time it is giving 0. So this forms a basis for 2-qubit system. Why? Because we can write any states in terms of 5 plus, psi minus, psi plus and psi minus. How we can do it? So understand this thing is clear. Computational basis of 2-qubit system are this 0, 0, 0, 1, 1, 0 and 1, 1. But we can have another basis states. Those are 5 plus, 5 minus, 5 psi plus, psi minus, and they are forming a orthonormal basis. And we can write any 2-qubit state in this basis. So how we can do it? Just see here. Computational basis, we write the state like this, alpha times beta times 0, 1 and like this. But we know that 0, 0 is what? So from this, so these 4 states are there. If I add these states, first and second, if I add these 2 states, then what will happen? This thing will cancel out. So what we will have? 0, 0 state we will have. So we can write this 0, 0 states in terms of 5 plus and 5 minus. So 0, 0 will become 5 plus plus 5 minus. So is the whiteboard content visible to everyone?
Yes, it's
Participants?
visible.
Okay, someone is so okay. Partly visible. It's visible. Okay, so it's visible. Maybe some of you are having issue, but it's visible. So what we are trying to say here is that we can write this computational basis state 0, 0, 0, 1, 1, 0, and 1, 1 in terms of these four basis states of Bell states. So for that, what we do is we just add this first and second. So we get 0, 0 in terms of 5 plus and 5 minus. Similarly, you are getting 0, 1 as a combination of 5 plus and 5 minus. Oh, sorry, psi plus and psi minus. And likewise, you will get. So what we can do is instead of 0, 0, we can write 5 plus and 5 minus, and then we can rewrite the state like this. So it will become like this: 5 plus 5 minus psi plus psi minus. So what are our basis states here? Those are these four basis states: 5 plus 5 minus psi plus psi minus, and this we call as a 2-qubit state in terms of Bell basis. These four Bell bases are there, and if we want to measure the state in Bell basis, then the way is the same. How we can measure the state in Bell basis? So there are four Bell bases. So when you are going to measure in Bell basis, then what will happen? So maybe I can write it here itself. So this is the your state. So psi 2, if you want to measure psi 2 state, you want to measure in Bell basis. So then what you will do is you will inner product with 5 plus 1 time. So that will give you the probability of measuring this state in getting in 5 plus. Similarly, for 5 minus and psi minus and psi plus. So what we will do is we will measuring it with four this basis states of Bell states and do the inner product and then mod square. That will gives us the probability of getting the state in 5 plus state. Similarly, probability of getting in 5 minus state. So, and what will be the term will come out? So when you do the inner product like this, then the term will be like this: probability of getting in 5 plus is alpha plus beta by root 2 mod square. Oh, sorry, yeah. So what I'm telling here is that we can do the measurement in Bell basis also. So for Bell basis measurement, this is the way we can perform inner product with these four basis states, and we will get the measurement. So on measurement, okay. So now what we are trying to say here is, suppose we do not have Bell basis to measure. Suppose we have only Z basis only. Yeah. So the two qubits are there, and we want to measure them in Bell basis. So instead of measuring them in Bell basis directly, can we do the same thing which we did for Hadamard X basis? We do. So what we did is we have only this Z basis for measurement. So to convert this Z basis results into Bell basis, you need to apply some unitary or some quantum gates before it. And if we apply this unitary, control knot and Hadamard, then this thing becomes Bell basis measurement. Okay. So what we are trying to say here is that instead of doing the measurement in Bell basis, we can manage with Z basis also. And for that, Z basis conversion to Bell basis, you need to apply some quantum gate. And for Bell basis, these gates are control knot and Hadamard. You just remember from that Bell state 5 plus state. So to create the Bell state, what we do, we apply the Hadamard and then we do apply the control node. So just we are trying to nullify that effect. You remember when we create Bell state, so what we do is we apply the Hadamard gate on first state and then control node. So we are just doing the reverse thing here, and that reverse thing will give us the measurement in Bell basis. And what we will measure, suppose if we are measuring 0, 0, then it means we are having measurement of 5 plus state on measurement. So we do the measurement in Z basis. We are just applying these two gates before that, and we are saying that if we measure 0, 0, then it means the Bell basis measurement is 5 plus state. If we are measuring 0, 1, then Bell basis measurement is 5 minus, and likewise. So what we are trying to say here is that any kind of basis you can measure in with the help of Z basis measurement and some quantum gate before that. So for the Bell basis measurement, you just need to apply the control knot and Hadamard, and that will give you Bell basis measurement. And how you will interpret the result of the measurement. So when you measure at this thing 0, 0, then it means the Bell basis measurement is 5 plus, and likewise. You know also that we create this 5 plus state when we initialize the, okay, some confusion is there, no problem. So if you remember, so to create the state like this, 5 plus, how you create the 5 plus state? We do the Hadamard and then control node. So what we are saying is that this part we are doing reverse here. So this control node we are applying first and then Hadamard, and then we doing the measurement in Z basis. And since we initialize with 0, 0, so we are saying that this is 5 plus state. Suppose if we are initializing with 0, 1, 1, 0 here, then what we will get here? Here we will get minus thing, and that will be our 5 minus. So what we are saying is that if we are measuring 0, 1, that means we are measuring 5 minus. Okay. So let me summarize this thing again for you, everyone. So we can write these qubit states in a column vector form, and in Z basis, we just write the coefficient alpha beta. And when we want to measure in particular 0 or 1 state basis or Z basis, so what we do is we do the inner product with psi state in 0 and 1. So that will give us measurement in Z basis, and 0 and 1 probability we will get. If you want to measure in X basis, then what you will do? You will be again doing the inner product with what? Plus and minus state. So inner product with plus and minus will give you the measurement in plus and minus basis. And that thing we can implement with the help of just applying the Hadamard gate before Z measurement. That will give us the measurement in X basis. Okay. So what we extend here is that Hadamard plus Z is nothing but X only. So there is this equality is there. So either you do the X basis measurement or you just apply Hadamard and then Z, that will give you X basis measurement. So, and that then we explain that for a 2 qubit system in computational basis, it is written like this. Okay. So this 2 qubits in computational basis 0, 0, 0, 1 and 1, 0 and 1, 1 is like this. And we can rewrite this in terms of basis states from Bell states. So there are 4 Bell basis states, and we can rewrite the computational basis 2 qubit state into in terms of Bell basis, and that will look like this. Okay. So the state will look like this. And in this Bell basis, what we do is, if you want to measure in Bell basis and you want to find the probability of getting 5 plus, then what you will do is you will do the inner product with this state of 5 plus and 5 minus and 5 plus and psi minus to get the respective probabilities. So in place of doing that thing with the measurement, you do not want to do the Bell basis measurement directly, separately. You can do it with Z only, but before that you will apply this gate control knot and Hadamard, and that will give you analogous to Bell basis measurement only. And you can interpret the results like this. If you measure 0, 0, then you say that we measure 5 plus in Bell basis, and 0, 1, that means 5 minus, and likewise. So with the Z basis only, we can do any basis measurements. Just we need to apply a unitary before the measurement. So far any question is there, then we can move to next topic of our talk is quantum teleportation.
There is one request from Monisha saying, could you repeat? So, Monisha, if you can post the particular topic which you want him to repeat, it would be helpful because it's not clear. So, it was posted 5 minutes ago, 5 to 6
Yeah.
minutes ago.
So Monisha, is it clear now, or maybe you can just pinpoint where to highlight or repeat? Unitary before is not clear. So just understand with simple example of
So
just a second. There are many questions. Could you please show the cursor when you are okay? Okay. So the thing is like okay. So the cursor is not visible most of the time. So just focus here. The
maybe
cursor
you can zoom your notes a little bit
screen.
because it's
Yeah.
yeah, yeah,
Is it okay now?
yes.
So what we are trying to say here is that Z basis measurement is pretty much clear. And if you want to measure in X basis, so suppose if you don't have this X basis measurement capabilities or devices, then what you can do is you just apply a Hadamard gate before the Z measurement, and that will give you the measurement in X basis. So with this Hadamard application, you can convert the Z basis measurement into X basis. And you can convert to any other basis also. Just you need to apply the corresponding unitary or the quantum gate before the Z measurement. And for Bell basis measurement, for 2-qubit system, this unitary is this is the unitary control node from first to second qubit and then Hadamard. It is just exactly the reverse when we used to create the Bell state. If you remember from this 5 plus state. So the 5 plus state creation, what we do is we apply the Hadamard and control node. Even not for 5 plus, for every Bell state. So just we change this input. So for 5 plus, we keep this 0, 0. For 5 minus, we keep it 1 and 0 and 0, 1 and 1, 1. So using this different values of these two input qubits, the circuitry remains same here. What is the circuitry? Hadamard and control node to create the Bell state. So suppose if you want to measure in Z basis with the help of Z basis, then what you do is just apply the reverse of it. So reverse of it is what? So this control, so this is used for creation of Bell states. So we just apply these gates in reverse order. So control node and then Hadamard. Then if we measure 0, 0, that means we measured a Bell state 5 plus. If we measure 0, 1, then we say that we measure 5 minus. Why? You will see, observe here also. So if we do the 5 plus here, so 5 plus we initialize with 0, 0. For 5 minus, we will be initialized with 1 and 0. For psi plus, we will initialize with 0 and 1. And psi minus will be 1, 1. So these four inputs are there. And what we are doing is just Hadamard and control node. So we are just inverting them and then doing the Z measurement. So on Z measurement, if you observe 1, 1, then it means uh, your input were 1, 1 here and you created psi minus state. So what you will tell simply is that we are doing the Bell basis measurement with this circuitry, and if we observe 1, 1, that means we measured phi minus. Is it okay now? Okay, then maybe we can continue. If any other doubts, then we can address later on also. So let's move to the quantum teleportation part, which is one of the important thing to cover today. So is my screen visible to everyone? Is the screen visible? Slides visible? Yes. Okay. So just now what we have seen is that any basis measurement can be done with the help of Z basis measurement. Just you need to apply some unitary. So that is okay. Now let's pay attention again for the new topic, that is quantum teleportation. In quantum teleportation, this thing what we will try to cover is, first we will understand what exactly quantum teleportation means, and then we will see the how we can implement this quantum teleportation using quantum circuits, and we will see the derivation that how this is happening. So with an example we will understand. So in quantum teleportation what happens is that Okay. So in quantum teleportation, what is our goal is basically? Our goal is that Alice, uh, Alice, one sender is there and one Bob receiver is there. So Alice want to send this qubit psi. The qubit psi is alpha times 0 plus beta times 1. And even Alice does not know what is alpha and beta inside. Just know that some quantum bit or qubit is there in state psi. She has this qubit psi, which is alpha times 0 plus beta times 1. He want to transfer this state psi to Bob without actually sending it. So what Alice want to do is she want to send this state psi or the qubit psi to Bob without actually sending it. She want to create psi here with the Bob. For that, what we are saying is that they have already shared Bell state qubits or entangled pair of qubits. So if you remember from previous sessions, this state is nothing but it is what? Beta 00. So it is beta 00. So what we are saying is suppose it has been implemented by two photons, P1 and P2. So what we are saying is that initially with some process like SPDS, we have created this entangled pair of photon P1 and P2, and their polarization entanglement property is like this, that if both are having horizontal polarization, that is we are denoting as 00, or vertical polarization, that is we are denoting as 1, 1. So this kind of uh, Bell pair or entangled photon pair, suppose they have created, and after the creation of these photon pairs, what they are saying is that P1 is with Alice and P2 is with Bob. Okay. So what we are trying to say here is that uh, P1 P2 photon entangled pair was there, and one part is with Alice and one part is with Bob. So this is we are assuming that Alice and Bob has P1 and P2 already. With the help of this entangled pair, Alice want to send this state psi, and without actually sending it, what will happen at the end of this protocol is that Alice is not sending it physically, but at the end of this quantum teleportation, this qubit P2, it will become psi. Okay. So what we are trying to say here is that Bob and Alice has P1 and P2 photon. Those are basically entangled pair of photons. And Alice has another photon psi, and its state is alpha times 0 plus beta times 1, that she want to recreate at Bob's site. So how this recreation at the end of the protocol will happen is that Bob's photon P2 will become psi. So we are not actually physically sending this qubit to Bob. We are just recreating the similar psi state here. So is this thing clear? Any doubt is there? Because the crux we need to understand what we are trying to say here is. Can anyone summarize it? What we want to say here is. So it will be clear to everyone. Just unmute mic and they can tell. Professor Mehrabal, mic is on for participants, or are you able to unmute and talk, or participants? So, Sodanya, can you, okay, maybe with chat only. Okay, so not that feature. Uh, Professor Mitharwal, can you unmute the participants? So anyone, if they are able to unmute and can tell for everyone what we are actually doing it in quantum teleportation. We are not sending the qubit physically. What we are trying to do is we are trying to recreate the state psi at the. Okay, Monisha, you write it correctly. So the thing is clear to. So the question was what exactly in quantum teleportation we are doing. So in quantum teleportation, Alice, so this part is Alice and Bob has entangled pair photon and P1 and P2 with them. So P1 is with Alice and P2 is with Bob. And now Alice want to send another qubit or photon psi state, psi qubit to Bob. So it is not actually sending psi physically here. This is basically a photon. So Alice is not sending the photon, but trying to recreate the state like alpha times 0 plus beta times 1 for this photon psi state here. So only the state psi is being created, and which is exactly same as psi in the photon P2 will be created at the end of the protocol. So we are not sending the photon physically in this process. What we are doing is uh, we are creating a state similar to psi in photon P2. So let's begin with the protocol. So how many qubits we have? We have 3 qubits. Two are basically entangled pair and one is the Alice psi qubit. So just we are saying that this first qubit psi is there and then this Bell pair. Okay. So this is one already explained. So in the protocol, what we do is Alice do some computation at her site and then she measure her qubits. So Alice has these 2 qubits. So Alice will do some computation on her part and then measure, and then the measurement outcome. So this 2 qubits she will measure and it will tell the measurement outcome to Bob, and Bob will apply some operation on his qubit and then his qubit will become psi. So this is the exactly protocol is. It will be more clear with the circuit diagram. So just understand here. Okay, maybe. So just see here. This is the psi state, that is alpha times 0 plus beta times 1. This state they want to teleport here. So what Alice will do is, and if you remember, this is beta 00. It is what? 00 plus 11 by root 2. So it is consist of two photons. Let's suppose P1, P2, P1, P2. And what we are saying is that this is qubit 1 and these two qubits are Q2 and Q3 qubits. Or maybe we can write them as a P1, P2. So Q2 and Q3 qubits are here, and this part. So this part is at Alice side and these thing are Bob side. So what we are trying to see here is Alice want to send this psi. So Alice has this psi qubit with her, and Alice also has Q2 and Q3 are entangled pair. Yes, Monisha. This Q2 and Q3 are entangled pair. We already created. Okay. That is beta 00. So either both will be 00 or both will be 11. So that is the entangled state we are using here. Now what we are saying is that this Q2 is with Alice. So this entire part in red color here is, it is with Alice. And this part is with Bob. So Alice has qubit Q1 and Q2 with her. Then what she is doing is she is applying these two gates, control NOT and Hadamard gate. And if you remember from the previous session, if we do the control NOT gate and then Hadamard, control NOT and then Hadamard, and then applying the Z basis measurement. So this thing is called what? It is called Bell basis measurement. Bell basis measurement. Okay. So just to tell that, but what LS is doing is basically she is applying the control NOT and then Hadamard and then measuring in Z basis, that is equivalent to Bell basis measurement. So on measurement, Alice will measure two qubits M1, two bits M1 and M2, and those are denoted by this double wire. That means the classical bits. So these are basically classical bits. So it will measure two classical bits M1 and M2 at her side. Now what this Alice will do is, Alice will tell this M1 and M2 bits to Bob on classical channel. Now what Bob will do is, Bob will apply X and Z gates depending upon values of M2 and M1 on his qubit Q3. So his qubit Q3, what Bob will be doing is, on his part of qubit 3, he is applying X gate and Z gate depending upon the value of M1 and M2. So this M1 and M2 can be either 0, 0, 0, 1, 1, 0 or 1, 1. So suppose if these two are 0, 0, then Bob will not apply anything. And if it is 1, 1, then Bob will apply X and Z gate on his qubit. And after application of this operation, his qubit becomes psi. So understand here, Bob was having the part of entangled pair qubit Q3 with him, and if we apply the X and Z gates, yes, these gates are fixed. We will see that why this gate will give us give Bob psi. So Bob is applying X and Z gate depending upon the value of M1 and M2, which Alice shares and which she gets on measurement here. And if Bob apply X and Z gate, then Bob's qubit Q3 becomes psi. And that is the purpose of the protocol. So what was the purpose? We want to teleport this state psi here. So basically we did not send this qubit psi here directly, or this qubit Q1. Qubit Q1 we did not send it here, but what we did is, Alice does this Bell basis measurement on her qubits, and then she shared the her measurement outcomes M1 and M2, which are two classical bits, and these two classical bits she shares to Bob, and Bob apply X and Z gate depending upon the value of M1, M2, and after application, Bob's qubit becomes psi, or Bob's qubit has same alpha and beta. So Bob's qubit Q3 becomes psi means it is having a state like this: alpha times 0 plus beta times 1, and which is nothing but psi only. So for any question is there in understanding the high level idea? Just write down in chat so that I can see. Okay. Yeah, so the question is, how will Bob know to apply X and Z gate? So depending upon the value of M1 and M2. So if M1 and M2 are 0, 0, then this gate will not be applied. If M1 and M2 both are 1, 1, then X and Z will be applied. So we will see in the derivation how it is derived. Then you will be convinced that this application of X and Z gate, depending upon the value of M1 and M2, will recreate psi state here. So let's go into detail. So, and just you want to derive that this state at the Bob's part, psi 4 is exactly psi or not, we will derive. So see here, initially what we are trying to say here is that this part in blue, this part is with Alice and this part is with Bob. This thing is clear, and there are three qubits, Q1, Q2 and Q3. This is your Q1, this is your Q2 and Q3, and they are part of this, they are entangled. Okay, entangled. And entangled means beta 0, 0 is nothing but 0, 0 plus 1, 1 by root 2. Okay. So what Alice is doing is, so initially what the state of combined system is, this three qubits we are writing as, sorry, this is qubit 3. So Q1, Q2 and Q3, three qubits are there, and Q1 and Q2 are with Alice. So what Alice is doing is, so initially if you see at the psi 0 means initial state at this point is psi 0, and psi 0 is nothing but first qubit psi and second and third qubit are beta 0, 0. So this is nothing but Q2 and Q3 is beta 0, 0, and beta 0, 0 also we can rewrite like this: 0, 0 plus 1, 1 by root 2. So psi 0 is nothing but alpha times 0 beta times 1 plus 0 0 plus 1 1 by root 2. So this is our initial state psi 0, and just we multiply it. So on multiplication it will become like this: alpha 0 is multiplied with the 0 0 part and 1 1 part, and beta 1, this part is multiplied with the entire thing, and this part multiplied with the entire thing. So we can write psi 0 like this. So far any issue is there? What we just did is we just write the beta 0 0 expression and just multiply and rearrange it like this. Now what we are doing is uh, okay, so just again multiply it. So this thing is become this. So just rewrite it. Now what we are saying is that we are applying control node from first to second qubit. So just see here, control node from first qubit to second qubit. So what control node does is, if you remember from previous days session, control qubit and it is target qubit. So when control is one, target is, or t become t dash. So just see, this was the state psi 0, and you want to apply control node from first qubit to second qubit. So this is your first qubit, and this is your second qubit. This is also second qubit, second qubit, second qubit. This is your Q1 here. And in that expression also, this is your Q1 and this is your Q2. This is your Q2. Is this thing are visible, participants? Q1 and Q2 I'm writing is visible. Okay. So just understand here. Yeah. So Q1 is there, first qubit is this. So since this Q1 is 0, so it will not change Q2. So they will remain same. So this first part will remain same. But in case of the second part here, Q1 is 1. So what will happen? It will flip the target qubit Q2 from 0 to 1. See here, it become 1. Is it visible? Yeah. So this become 1, and this 1 will become 0. So see here, because the control qubit Q1 was 1, so it flipped this 0 and 1 states to 1 and 0. Is this thing okay? So first step is clear. We apply this control node gate. Now what we are doing is we are applying the Hadamard gate on the first qubit. So just see here, Hadamard gate on qubit 1. So this is the expression state here. So which is the first qubit? This one. This one is first qubit part. This one is also first qubit part. So Hadamard on 0 will become what? 0 plus 1 by root 2. So this thing will is nothing but Hadamard on 0. So just recall from previous day. Hadamard of 0 is nothing but 0 plus 1 by root 2, and Hadamard of 1 is nothing but 0 minus 1 by root 2. Okay. So this 0 becomes 0 plus 1, and this 1 becomes 0 minus 1. Okay. And square root 2 part is multiply with the square root 2, so it becomes 2. So far, okay. So what we did is we just apply control node and Hadamard gate, and we get this state. Now what we are doing is just we are rearranging the qubits, because what we are trying to do here is, if you remember from this, Alice is trying to measure the first and second qubit, Q1 and Q2. She want to measure. So because this gates has been applied and she want to measure Q1 and Q2. So we will just take the, we will arrange this expression in such a way that we want to take the first and second qubit out. So just we are rearranging, and we will try to take the first and second qubit out. So here first is multiply with the second and third qubit. So we just multiply it everything. So on multiplication, 0 with this double 0 will become triple 0. 0 multiply with double 1 becomes 0 double 1, and 1 multiply with 0 0 is become 1 double 0. So just multiply it like that. Now what we are doing is just we are taking the states together which has first two bits are same. So here it is 0 0. So we are looking for another state which is having first two qubits as 0. So this is also the having first two qubit 0 0. So just we are taking this part and this part together. So If you see here, it is alpha time 000. So just here. So just come here. So what we are trying to do here is alpha 000 is there, this is there, and this part beta times 001. So we take together this. Now this 2 has been out. Now what we are trying to do is we want to take the first 2 qubits where 01 is there. So here 01 is here, and another state where 01 is there. So here it also 01. So these two we are taking together, this and this part. So it is alpha times 011, beta times 010. And likewise 10 is here, 10 is also here. So we are just taking them together. These two are here. And lastly, there 11 is there. So just we are rewriting such that this first 2 qubits we can take common out. Now we can take this first 2 qubits 00 common. So what it will become? It will become 00, and then inside it will be having third qubit is alpha times 0 plus beta time 1. Now we are taking common 01 here. So 01 is out, and inside we are having alpha times 1 beta time 1, and likewise. So any questions so far, participants? Previous slide, okay. Yeah. Now what is the question? Any question? You want to check zero state? So what we just did is just we initial state psi 0 we rewrite, that was there, just rewrite it. Then we apply the these two gates, control not gate and Hadamard gate. So we did that, and then we just rewrite, multiply and rewrite in such a way that we want to take common the first 2 qubits out, because okay. So what we did is just we take this first 2 qubits like 00 you want to take out. So for that we do this arrangement here. So after taking the 00 state common here, inside the third qubit is nothing but alpha times 0 plus beta time 1. And likewise, if we take this 01 common out, then alpha times 1 plus beta time 1 we are getting inside. So see here, this psi 2 has become like this. And what we are saying is that now this Alice is measuring this first 2 qubits. Okay, first 2 qubits, and she is calling the result as M1, M2. So if you measure this state, then what you will get? You may get 00, you may get 01, you may get 10 and 11. And probability of getting this 00 state is what? The coefficient, half. So probability of getting 00 on measurement is 1 by 2 mod square. That is 25%. And it is same for 01 state also, 25%, and same for other states, because the coefficient is 1 by 2 for every state. So Alice can get either 00 or 01 or 10 and 11 with equal probability of 25%. Okay, no problem so far. So Alice can measure M1, M2 as 00, can measure as 01, can measure as 10 and 11. Suppose we take the first case. Alice measure M1 and M2 as 00. So in that case, what will happen? Alice will measure this state 00. That means they will not happen. So third qubit will collapse to what? In that case, Alice measured this first 2 qubits, Q1, Q2, and this entire thing is Q3. And that is superposition of 0 and 1 state. So see here, first 2 qubits are measured 00. Then what is third qubit Q3? Third qubit Q3 is alpha times 0 plus beta time 1. And it is nothing but what? It is nothing but what? It is psi only. Alpha times 0 plus beta times 1. See here, suppose Alice measure 0, 0. In that case, Q1 and Q2 are 0, 0, and Q3 is nothing but psi only. So 0, 0, and it will tell Bob. What it will do is, it will tell Bob that I measure M1 equal to 0, M2 equal to 0, and then in that case, what Bob will do? So if it is 0, so it will not apply it. M1 is M2, both are 0, 0, so it will not apply any gates. So x power 0, that is nothing but, so if M1 and M2 are 0, in that case, this gate will not be applied. Okay, or basically identity will be applied. So identity will keep the state same. So in that case, when Q1 and Q2 are measured 0, 0, Bob will not apply anything on his qubit Q3, and it is nothing but psi only. And psi is the state which Alice wanted to teleport. Is this thing clear, participants? Or maybe request Professor Mitharwal to unmute the participants so that they can speak if required. Okay, so this was the case, but we can measure. Yeah, so understand here. So if measure 0, 0, then no problem. No need to apply any gate. Bob will automatically get the state psi. But if Alice measures M1 as 0 and M2 as 1, then what will happen? So in that case, suppose if Alice measures 0, 1, so it means this is the state which was prevailing. So if it measures 0, 1 first 2 qubits, then Bob's state Q3 is what? Alpha times 0 plus beta times 1. So what is the Bob state? If you see here, Bob state is alpha 0 and beta 1, alpha 1 and beta 0. And if you remember, if Bob apply Z gate on this state, sorry, X gate, because what Bob is getting is alpha times 0 plus beta times 1. And if Bob apply X gate, and what this X gate does is, it changes 1 into 0 and 0 into 1. Just kind of complement it does, not operation, it does. So Bob's state is alpha times 1 plus beta times 0. But this is not equal to psi, is not equal to psi. See here, psi is alpha times 0 plus beta times 1. But here we are getting the opposite thing, alpha 1 and beta 0. So if Bob apply X gate on his qubit, then this 1 will become 0, this 0 will become 1. And now this thing is psi only. Are you getting this thing? So if Bob apply X gate on his qubit, then his qubit becomes psi, which Alice wanted to teleport. Is this thing clear? Okay. So there may be another case, because this measurement outcomes are equal likely, and with 25% probability, Alice can measure 1, 0 also. Suppose Alice measures 1, 0. In that case, which state will prevail? So if Alice measure 1, 0, then this is the state Q3 Bob will have. So Bob Q3 is nothing but alpha times 0 minus beta times 1. So what is the Bob's state? Alpha 0 minus beta 1. And that is not equal to psi. Just this sign change is required. If this sign minus L minus beta 1, if it becomes plus, then it will have the psi state. So to change the sign, we apply the Z gate. And what this Z gate does is, if you just want to understand, Z gate when you apply on 0 state, it will remain same. Z gate when apply on 1 state, it become, when you apply Z gate on this, it becomes -1. So see here, when we apply the Z gate, this 0 will remain same, this 0 will remain same, but this 1 will become minus 1. So minus minus, it will become plus. So if Alice measure 1 0 and she share this information that I measured M1 and M2 as 1 0, then what Bob will do? Bob will apply the Z gate on his qubit Q3. Then his qubit Q3 alpha times 0 minus beta times 1 will become psi only. Okay. Suppose Alice measures 1 1. So in that case, Bob's qubit will be what? This will be Bob's qubit. So Bob is having alpha time 1 minus beta time 0. So in that case, since both M1 and M2 are 1, so Bob will apply the first X gate and then Z gate. So if we apply X gate, then it becomes 1 becomes 0 and 0 becomes 1. So yes, I can write it here also. X of 0 is 1, X of 1 is 0. So X gate will flip this 0 into 1, 1 to 0. So this is the state. Still it is not psi. So just we need to apply the Z gate. So that will change the sign and it will become plus. So see, it becomes psi. So see here, depending upon the value of M1 and M2. If M1 and M2 are 0, 0, then it will not apply these gates. So basically, X power 0 will become identity. So it will be applying identity. So whenever these both are 1, then this both X and Z gate will be applied. And see here, this importance of M1 and this ordering is important. You will first apply X gate and then Z gate. If you do in reverse order, then it will not become psi. See here. Here this ordering is important. First you need to apply X gate and then Z gate. If you do it other way, then it will not be equal to psi. So what we have seen here is that whatever the qubits measurement outcome Alice gets, either she can get 0, 1, 1, 0, whatever she gets, she will share this 2 bit of classical information to Bob. And then Bob will apply this X and Z gate depending upon the value of M1 and M2. And then his qubit Q3 becomes psi at the end of the protocol. Is it clear to everyone? Participants? I want to take some questions here so that things will be clear to everyone. Any questions so far? So question is there, then just write the question so that I can answer. I am seeing the chats also. Okay, so there is no question. So whatever we have done here, we can see this thing on through quantum programming also. So let's just try this thing on Qiskit platform. So yesterday also I explained this platform in a bit, but yesterday we were in hurry, so we could not see that thing, but we can see now. So Prahlada, any question particularly you can say, then I can answer. Prahlada says not clear. So just to recap, because this thing should be clear to everyone. So we were having 3 qubits, Q1, Q2, and Q3, and Q1 was having state psi, which Alice want to teleport to Bob. At the end of this protocol, the entangled qubit part Q3 will become psi at the Bob side. So ultimately, this state psi is being teleported here. But remember this thing, that physically psi is not been sent here. Just this Q3 has become psi. The Q3 qubit has become psi at the end. So we are not physically sending it, but the properties of this state Q3 becomes okay. So okay, so maybe you can write the queries. So ultimately at the end, what we are trying to do here is that just we want to teleporting the state psi from Alice to Bob. with the help of this two untangled pair of qubits Q2 and Q3. And in that process, Alice do the Bell basis measurement, and she shares the output of that measurement M1 and M2, two classical bits, to Bob. And depending upon the values, Bob applies the gates X and Z, and ultimately Bob gets psi at his end. So okay, we can try this thing on Qiskit. So yesterday I have shown you guys that platform Composer, wherein you can graphically see these things. Just you remember from previous the session. So you can try those things graphically also. And there is another elegant way to do the thing using Qiskit programming, wherein Python kind of interface programming is there, and using that Python programming, you can program quantum computers and quantum simulator both. And I explained that yesterday that if you create an account on IBM website, then with creation of account, you will get 10 minutes of free QPU time. Means you will have 10 minutes run time for the quantum processors. So the see here, these devices are freely available and you get access to them without any price. Okay. So, and then you can experiment on those processors. And yesterday also I shown you the results of this Bell state creation, if you remember. So in the Bell state creation, you remember, ideally we should get 0, 0 and 1, 1, but we are getting this thing because the actual QPU has errors. So you can do experimentation here, and it's very easy to learn because everything is graphical here. You do not write any programming instruction. So you can learn with the Composer platform available here. But in the Composer graphically, what you have seen is that you need to write every instruction, you need to drag and drop this thing. So see here. So the problem is that you need to drag and drop every gate here. So that's a not an elegant way to do the programming. So you can just need to drag and drop every gate for everything. But there is another way that is called Qiskit. So you can download this Qiskit library and install it. And I have installed it for Visual Studio, and in which so Prahlada has asked that what I have shown yesterday. So yesterday we have seen that Composer part. Okay, just a second. So these are the devices, quantum devices available on the platform, and some of the devices which are shown in green are available on which you can run your quantum circuits. And here in the quantum composer, so just search this term composer, so you will get this interface. And herein what we have shown yesterday is that you can graphically drag and drop the gates here. So these horizontal lines here denotes the quantum bits, and these are the gate set or the basically quantum gates. Using those, you can create quantum circuits. So everything is graphical here, and you can add, delete quantum gates and everything. And so here, okay, so here what we have done is we created the Bell state, and you need to measure those qubits. So for measurement, we can apply these gates, and whatever gates you create here, you can run them on QPUs. So just click on that button, which I have shown here. Are you able to see that button? This QPU button. So just click on that button and you will be shown that these are the quantum computers available. So see here, IBM Torino is available. So just see the highlighted part. So if you want to run your circuit on this, then you can just click on run this circuit on Torino. And you can also share that how many times you want to run this circuit, because the results are probabilistic. So if you run it for 1024 times, then 50% time you should get 0 0 state, 50% time you should get 1 1 state. But when we actually run it, so I have already run it and share you the results. So maybe you can run it right now itself. When you just submit this job, you can see the job details here. So see here, at this time I have submitted the job and it is in progress. So it is being run on the IBM Torino quantum computer. So once it is run, you will be notified here. So I have already shown the results of already run instances like this. And we were expecting that there should be no 0 1 and 1 0 state ideally. But these are occurring because of noises that we have already discussed. So this is a way to do the thing graphically, and there is an elegant way to do the things programmatically. So that is being provided by the Qiskit platform. So I have installed the Qiskit library. That Qiskit is this name QISKIT. So this library, if you install, then with Python programming, you can write your quantum algorithms or applications faster. And for quantum teleportation, we would like to. So okay, so Ballister also we can use create using this. Okay, just recap the thing with Ballisters. So what we are doing here is just we are importing the libraries in the first phase here. So we just imported the libraries which are useful for us, and there is this air simulator is there. That is basically it gives you a simulator kind of environment wherein you have perfect qubits or logical qubits. So you will get the noise-free results. Okay, when we run on actual QPU, there are errors. So we get erroneous results. But in air simulator, we assume that this environment is ideal. There is no error. So we get the ideal results. So just we are doing this. What we are doing is we are assigning or creating a quantum register with 2 qubits. And then we are creating a classical register with 2 bits. Then we want to create a quantum circuit which has QR quantum bits and CR classical bits. And it is named as circuit. We can draw this circuit with this command circuit.draw. So it will draw the circuit for you. And it will look like this. There are 2 qubits and there are 2 classical bits. So these are denoted by here. Now what you want to do is you want to just apply the Hadamard gate and then which gate? Control NOT gate. So see here, we are applying the Hadamard gate on the first qubit, that is QR0, and then we are applying the control NOT that is noted by CX. So CX means control NOT gate from qubit 0 to qubit 1, means first qubit to second qubit. So these 2 gates we are applying. So just we write this command circuit.h will apply the Hadamard gate on the qubit 0, and circuit.cx will apply the control NOT from qubit 0 to qubit 1. So we can also see the circuit. So once we write these 2 gate instructions, these gates are applied. Okay, and just rerun it again. So what we have done is Hadamard and then control NOT. So this is the circuit has been created. And just we write this one line circuit.measure. So what it will do is it will measure this quantum registers into classical register. So these quantum bits are measured in classical bits because we cannot see the quantum results inside it. We need to measure them in classical and then we will understand the results. So this is doing the measurement and we will get classical outputs. So these measurement gates are applied. Suppose if there are 10 qubits, then you need to apply this measurement 10 times graphically in the composer thing. But here Just one line, circuit.measure will do the thing. Now what we are doing is we are calling the backend air simulator. So means backend means where you want to run this quantum circuit. So this backend can be quantum Torido. This was quantum computer. You can use as a backend. Whatever quantum simulator or QPUs are available, you can use for backend. So here what we are doing is air simulator you are usually using, and that is a local simulator. Means it will run on local machine. Okay. Now just we are running it. So backend we have taken air simulator, and this transpilation is required when we are running on actual QPUs. Why? Because QPU has their own set of basis gates. So whatever circuit you have drawn in your gates, it will convert them into native gates of the QPU supports. So whatever circuit you draw, it will create the circuit into native gates of the QPU. But here there is no transpilation required because we are working on simulator. And how many time you want to run? So just we put the number 1000, and then just we are doing running and just we printing the results. So see here, 1000 time we run the circuit, and we are expecting that probability of getting 0 and 1 1 is 50%. So almost 50% we are getting it. So we can just rerun it again. So then we will be seeing the different kind of results, but it is almost 50-50. See here, 494 time we are getting 0 0, and 506 time we are getting 1 1. So as we increase the number of shots, we will get almost 50-50 probability. So this is the ideal behavior we are expecting in a noise-free QPU. If noise are there, then you may get also 1 0 and 0 1. Okay. And if you want to run on actual quantum computer, then you can just put your account details here. Basically, some key they provide. So if you put this key and then write this thing, then you can run on QPU also from the Qiskit interface. So here also you can directly you can run on the Qiskit platform. So basically, the thing is that uh, you need to provide the key which is associated with your account, and then it will fetch the QPU from there and submit the job to QPU, and you will get the result back here. So far it is clear, participants? Okay. And similarly, we can create the quantum circuit for ZHZ state. So the 3-qubit entanglement state. So for that, just you need to put one C naught here, and then if you run it, then it will be like this. Either you will get 000 state or you will get 111 state. Okay. In the Z at Z state. Okay. So uh, let's break for 10 minutes, then maybe we can reassemble at 425, and then we will see the quantum teleportation and super dense coding. So any questions so far? Then we can address it right now, or maybe you can ask after we resume at 4:30. Okay, so we are taking break of 15 minutes, and we will restart at 4:30, and we'll do the quantum teleportation circuit on Qiskit, and then we will see super dense coding and its circuit. Okay. Okay. Yeah, so I will be sharing code and everything, so you can practice with those quantum circuits and the codes. So I will be sharing that. So I'm keeping my screen like this only. So after 30 minutes, we will Shall we start?
Yes, sir, we can start.
Okay, Akshay, you will be helping me.
Yes, yes,
Okay,
yes.
okay. So just now what we have seen is that we have seen the quantum teleportation circuit, and which was looking like this. So just recap from here. So yeah. So there were 3 qubits we need to have, and then we perform the Bell basis measurement, and then we are applying these gates on the Bob side. So what we are trying to do is we are trying to implement the same thing on Qiskit. So just for reference, I have shown you this thing. So this code is visible to everyone. So just we
Yes,
are
sir, it's visible. The screen is
yeah.
visible,
So what we
clear.
are yeah. So what we are doing is we need 3 qubits, one for Alice to transmit and 2 for entanglement pair. So we are declaring 3 qubit quantum register here, the first step, and then we need to measure these 3 qubits. So for that we require a classical register which consists of 3 bits. Then we are creating the circuit with 3 quantum bits QR and 3 classical bits CR. So this is circuit we are creating, and then by default these qubits are initialized with 0. So if you do not apply anything, then they are initialized with 0 only. So our first qubit, second qubit, and third qubit both are three are in 0 states. So that is the first part. And here what we are doing is we are trying to create a bell pair with this 2 instruction. So where we want to create the bell state in the second and third qubit. So they are basically qubit 1 and qubit 2. Second and third qubits are denoted by qubit 1 and qubit 2 respectively. So on the second qubit, that is Q1, we are applying the Hadamard gate, and from second to third we are applying control X gate. That will create bell pair between second and third qubit. So just we can see here. Okay, so let's print the circuit here itself. So what this part is doing. Okay, so just run it again. So see here, these are 3 qubits. Second and third qubit are here. Second and third qubit, and in the second and third qubit, we need to create a entangled pair. So for that entanglement creation, we are applying Hadamard gate on the second qubit and control node from second to third qubit. That will entangle second and third qubits. These 2 last qubits, second qubit and third qubit, will be entangled after this state, thus this state. And this is your first qubit that you want to transmit. So by default, it is initialized with 0. So suppose it is in 0 state and we want to teleport that. So 3 classical bits are there already. Now you remember from the circuit, Alice does the Bell basis measurement. So this thing is nothing but this entire thing. This thing we call as a Bell basis measurement. Control node from first to second qubit, and then Hadamard on first qubit, and then measuring them. So that is nothing but Bell basis measurement at Alice side. So for that, what we have to need to do is we need to just apply the control node from first to second qubit and Hadamard gate on the first qubit. So this part is see here, this part which we are showing here is your control node and Hadamard, and then you will be measuring them. So this measuring part. So this entire thing, second and third part, is basically doing the Bell basis measurement at Alice site. So although we are seeing these 3 qubits nearby, but in actual scenario, this last qubit may be far away on a different planet with Bob. Okay, so once they entangled with this first step of entanglement, and then they can take this qubit far away. Q2 and the second and third qubit can be far away. First and second qubit are with Alice. So Alice is doing the Bell basis measurement, and the measurement is done in the 2 classical bits. Now at the Bob side, Bob will do the control node and control Z gate. So this is basically what this gate is. Are you seeing my cursor on the gates, participants? Yeah. So at the Bob side, what Bob will do is, depending upon the measurement outcome of first and second qubit, if this second qubit is measured, and if it is 1, then it will apply the NOT gate on the third qubit. That is with Bob. If first qubit is measured 1, then it will apply the Z gate. So this plus and this blue dot denotes NOT and X and Z gate basically. So it will be applied depending upon the measurement outcomes at Alice side. So Alice measure this first and second qubit, and she shares these two inputs to Bob, and depending upon their values, Bob will be applying plus and Z gate on his qubit. And at the end, if Bob measures, so Bob will measure the third qubit, and this will be as first qubit. So in the circuit, if you see here, we initialize the first qubit with 0. See here. So by default, the qubit, first qubit 0 is uh, 0 only. So we should be getting the third qubit. So what is the third qubit here? Just see here. So on measuring this third qubit, so since this, okay, let me take this on, okay, copy. So I'm showing that circuit here. Just a second. I want to copy this circuit. Copy. And so this is your circuit. See here. So this is the circuit has been created. So this is the first part wherein this second and third qubits Q2 and Q3 are entangled qubit. This two are with Alice. This last one is with Bob. So Alice is doing this thing. This part is what? Bell basis measurement. Bell basis measurement. So in actual protocol, what will happen is this measurement outcomes M1 and M2 will Bob, Alice will tell this M1 and M2 to Bob. And depending upon the value of M1 and M2, Bob will apply this plus and Z gate on his qubit third. And at this point, this qubit 1 will come here. So it will be nothing but qubit 1. So initially the qubit 1 is 0. So Bob will also measure 0. Okay. So first scenario, that this first qubit is suppose 0. Then what should Bob get here? Bob also should get 0. So let's see in the outcome here in the program. So what we are expecting is that Bob should get 0. So Bob qubit is third qubit. So we are running on it on air simulator, and on running it, suppose 10,000 times we run it. So what should we get is third qubit should be always 0. So see here in the outcomes, we are getting state 000001 and this thing. So just a second, let me. So this is the outcome we get. Just a second. Just a new slide. Let me have a new slide. So this is the outcome we are getting on measurement. So just see here, this 3000, it means is this is your first qubit Q1, this is second qubit Q2, and this is Q3. So Q3 is 0 here, Q3 is 0 here, Q3 is 0 here, Q3 is 0 here. So every time Q3 is 0 only. So Q3 0 means Alice wanted to send 0, which is her first qubit, and Bob is measuring Q3 always 0. So although this qubit 2, qubit 1 and qubit 2 can be anything. Qubit 1 and qubit 2, if you see, sometime it is getting 0 0, sometime it is getting 1 0, sometime it is getting 1 1. But every time the qubit third that we are interested in. So we are not interested in every qubit. We are interested in the third qubit. That is this one. That is with Bob. Third qubit is with Bob, and that is always 0. That means Bob is getting 0 on at the end of the protocol. Okay. Suppose if Alice send 1, then what will happen? So to make this one, what we will do here in the beginning, we will apply X gate on the first qubit. So by default qubits are initialized with 0, and if we apply the X gate, or basically NOT gate, then it will become 1. So first qubit will become 1. So just run it again, clear all outputs and run all again. So see here, circuit is all the same. If you see here at the end, just first qubit we make it 1 by applying the NOT gate. So now what we want to send here, Alice want to send the first qubit as 1 to Bob. So at the end of the protocol, what Bob should get? Bob should get 1. So just see the results here. And if the results we copy there in the slides, and I can show it there. So these are the results this time we are getting. So see here, this is your Q3. This is your Q3, and that you are getting as 1. See, Q3 is 1 always. This is Q3, this is Q3, this is Q3. So it is always 1. It means whatever Alice wanted to teleport, she is getting the same thing. Or maybe we should not run it more time. We should run it 1 time only. So just see here. So shorts, if you keep it 1, then it will give you the correct thing. Just run it again, all. So see here what we are getting, a state 1 1 0. What it means is the qubit 1 and first qubit and second qubit are 0 1. Your third qubit is 1. So just let's again, just copy me. So see here, this is the third qubit, and that is 1. So see, this is qubit third, that is 1. Although the first and second qubit, those are 0 1. So as in the protocol also you have seen, if you remember from the protocol, this first and second qubit can be anything. Okay. So first and second qubit can be 0 0, can be 0 1, can be 1 0 or 1 1, whatever it is. But third qubit will always be the whatever we wanted to send. So as we have seen the result also, the first and second qubit can be anything. It can be 0 1, 1 0, 0 1, or whatever it is. Our last qubit will always be 1, which we wanted to send. So see here. Is it okay? Like, so what we are trying to say here is that in the third place, this is your third qubit, the below one, which will be, which is the same which we wanted to send. Okay. So here what we have seen is that first time we try to send 0, and second time we are trying to send 1. And in the both the cases, the protocol is working. So it will also work for a superposition qubit. Because what we are trying to send here is that we are sending as 0 and 1, and we are getting 0 and 1 correctively at the end of the protocol at qubit 3. But if we send an entangled photon, then we will get the same state here. So just to check the correctness, we are checking it with 0 and 1. And if it is working for 0 and 1 individually, then it will work for the combination of both 0 and 1 or superposition state also. So in actual scenario, what will happen in the protocol is that this So see here the circuit. So in actual thing, this Q2 part, this Q3 third qubit will be with Bob. Okay, and these two qubits will be with Alice. So this Q3 may be far away, and just Alice will tell this result outcome results, and Bob will apply corresponding gates and will get the first qubit at his side. So I think clear with the teleportation protocol. I will share the codes also. You can run it yourself and understand better. So can I move to the next session, the last session, that is super dense coding. If any question is there, then I can answer. Otherwise, we can move to super dense coding. Participants?
No question is there, so probably we can move to next session.
Yeah. Just a second.
So there is
The one
one
question.
posted. What is classical
Yeah.
bits?
So classical bits, as you know, it can be either 0 or 1. But in case of quantum bits or qubits, it can be superposition of both 0 and 1 simultaneously. So that is the key difference qubit has compared to classical. But qubits, when we measure them, we will get either 0 or 1 with certain probabilities that we have already seen. So I think it answers your question. So let's move to the last part, that is super dense coding. Yeah, so the qubits can be realized by different physical phenomena. You can realize the qubits. The question was that how we can uh, implement the qubits. So in hardware, most companies like Google, IBM, they do it with superconducting circuits. But there are another ways, ion trap and other ways, wherein you can have qubits. Even with a photon, you can implement qubits. So there are different ways to implement the quantum bits. So in super dense coding, what we are trying to do here is that suppose this Alice and Bob are in different part of the world. So Alice and Bob are far away. Alice is here, Bob is here, and Alice wanted to send two bits of information, B1 and B2, to Bob with the help of one qubit. Okay, so can she do it or not? So classically, what she wanted to do is she want to send two bits of information with the help of one qubit. So that is the thing Alice wanted to do in this protocol. So for that, we will be using the entangled pair of qubits. So we use this additional resource that we called as entangled bits. So we will have a pair of entangled bits between them, and we will distribute one qubit to Alice and one to Bob. And with the protocol of this superdense coding, we will be able to implement the transfer of two bits of information A and B to Bob. So this is the typically block diagram, which will explain the thing in detail here. So just I need everyone's attention. So there are three steps. One state is first one is that you need to prepare and share the states. So first what we are trying to do is Alice will prepare the states, Alice and Bob. So someone is preparing the bell pair. So this circuit is doing the bell pair creation that we have so many times we have seen. And this bell pair is nothing but it is looking like this. Beta 00 we write like this, and it will be 1 by square root of 2, and it is bracket 00 plus 1 1. So this kind of state it is, and it is maybe suppose if it is implemented by photons, then there are two photons P1 and P2, and this 0 and 1 is nothing but their polarizations. So these two photons P1 and P2 are here, and this circuit untangled them. And now what we are saying is that P1 is with Alice, or basically our sender Alice, and P2 is another photon that is going to Bob, or our receiver. So what we are doing is just we are creating the entangled pair here. One qubit we are giving to Alice, other qubits we are giving to Bob, and they are far away. Now Alice want to send bit information A and B. This A and B are classical bits, which can take values 0 and 1. So depending upon the values of A and B, suppose depending upon values of A and B, if A and B are 1, then it will apply Z and X gate on her qubit P1. So this P1 is with Alice. So Alice will apply Z and X gate on her qubits. If she wanted to send 00, then she will not apply anything. Okay. If she wanted to send 11, then she will apply both Z and X gate on her qubits. Okay. So if you just to make this thing clear, what this jet gate does, can anyone tell what jet gate does? Jet gate, if you apply on 0 qubit, it will remain same. It will be 0 only. And Z gate, if you apply on 1 state, then it will no. Z gate does the sign flip for 1 state. If it is 1 state, then it will change the sign. Phase flip, basically. Yeah. This is Z gate and X gate. X gate just flip it 0 to 1, and X gate of 1, it will become 0. Okay. And CX also, control not gate. What it does is, if there are 2 qubits, Q1 and Q2, then Q1 will remain same and Q2 will be flipped depending upon value of Q1. So if Q1 is 1, then it will flip the Q2. So what Alice is doing is, depending upon the bit value she wanted to share. So suppose there are 4 options. Depending upon this bit value A and B, so suppose she wanted to send 0 and 1, then she will apply the gates. Z she will not apply, she will apply only X gate on her qubit. Suppose she wanted to send 1 1, then she will apply both the gates. Then she will send this P1 to, no, this P1 will become P1 dash. Now she will send this P1 dash to Bob. So what basically Alice is doing is, Alice is just sending one qubit P1 dash, which is with her, and she just modified according to bit values of A and B and applying this Z and X gate. Now what Bob has? Bob has P2 with him and P1 dash with him. Now this is a circuit, if you remember, this is nothing but Bell basis measurement. So just understand, by this control node and this Hadamard and then Z basis measurement is nothing but Bell basis measurement, that is Bob doing on both the qubits P2 and P1 dash. And we are claiming that when this measurement is done, and this will be nothing but A and this will be B, which Alice wanted to send. So what we are saying is, if Alice encode this bits information by applying these gates and send her qubits to Bob, and Bob does the measurement in Bell basis, then Bob will get A and B respectively at his site. So using this protocol, we are able to densely encode 2 bit of information in single qubit P1 dash here and transferring it to Bob. So far this protocol's block diagram structure is clear. If not, then I can tell participants. Okay. So now we want to understand that why this Bell basis measurement and this step will exactly do it or not. So we want to just, yes. So to begin with, we need to have an entangled bit pair. So this is the prerequisite, that we should have an entangled Bell state pair, and one part of that pair should go to Alice and other part should go to Bob. Okay. So 3 steps. One step is this, when they prepare Bell pair. Second step, Alice encode the information A and B. And third step, Bob does the Bell basis measurement. And on that Bell basis measurement, how have Bob has sent P1 from Alice? No. This thing need to. This is a photon. Suppose this is photon. This photon needs to send to Bob, or maybe whatever the way you have implemented the qubit. So this P1 dash. This it will not be the P1. It will be modified after these two operations that we are calling as P1 dash. That somehow Alice need to send to Bob. So there may be any way by a fiber optic cable it can send this photon, or maybe through free space it sent to Bob, and Bob should able to receive and apply the Bell basis measurement on the qubits. So on measurement we are promising that this protocol will give us give Bob A and B. So we'll see step by step how this is happening. So the can you just tell the question exactly what you want to ask? Someone has asked some question. Maybe you can unmute the participant and you can tell.
It's how Bob has sent PI from Alice, and how
No.
Alice has sent the PI to Bob.
Okay, Prahlada, you said I answered it already. Okay. So basically what we are saying is that there are two qubits, P1 and P2. They both are entangled, and P2 is given to Bob in the beginning itself, and P1 is given to Alice. Alice encodes her bit information and then send the modified P1 that we are calling as a P1 dash to Bob. Now Bob has both P2 and P1 dash with him. Then he is applying the Bell basis measurement, and measurement outcomes are A and B respectively, which Alice wanted to send. So let's see how it happens. So these are the bits information. So we can derive it like also. So what we are having initially is that we are having a state like this: 0, 0 plus 1, 1 by root 2. So this is the state in the beginning here, 5 plus. Now what we are saying is, suppose Alice wanted to send, yeah, it is just analogous to teleportation, but the purpose is different. In super dense coding, we try to send 2 bit of classical 2 bit of information to Bob. In teleportation, we want to send a single qubit size state. So in that case, we wanted to send qubit. In this case, we are trying to send 2 bit of classical information A and B. Suppose Alice wanted to send this A is equal to 0 and B is equal to 1. This is the information Alice want to send. So this just see here, this line is showing this upper part is with Alice and lower part is with Bob. Bob is having the lower part, Alice is having the upper part. So this qubits has been created, and this first one part of the qubit is given P1 to Alice, and this P2 is given to Bob. Now what this Alice will do is, depending upon the values of A and B, it can be 0, 0, 0, 1, 1, 0 or 1, 1. These two bits can take these 4 possible values. Depending upon the values, Alice will apply the gates. Suppose this qubit is 1, then she will apply the Z gate. This -1 denotes Z gate. This denotes X gate. X gate. So in this case, Alice wanted to send 0, so she will not apply the Z gate. B is 1, so it will apply X gate on the her part of qubit. Okay, and you remember this thing that this part is with so this first part 0 and 1, this is with Alice. So now what Alice wanted to do is, Alice wanted to send 0, 1. So she will apply the X gate on her first qubit. So this is first qubit. So X gate, you remember what X gate does is, X gate will make it what? This 0 will become 1. This 1 will become what? 0. Second qubit will remain same. Second qubit, we are not doing anything. So what Alice has done is just apply the NOT gate on her qubit. So the first part P1 is with her. Is P1. The second part is with, this is P2. This is P2 with Bob. Now see here, this is the state after applying this gate. Now what we are saying is that this P1 has become P1 dash. So P2 is already with Bob. This P1 become P1 dash. Now this P1 dash is also sent to Bob. So Alice is sending this qubit P1 dash to Bob. Okay. So Bob is receiving it. So now this entire thing is with Bob. So this thing has come to Bob. Because P2 was already with the Bob in the beginning. Now P1 dash is also sent to Bob. So Bob is having this P1 dash and P2 with him. Now what Bob is doing is, Bob is applying control node and Hadamard gate and then doing the measurement. So this control node is from which gate to which gate? From the P1 dash to P2. So this qubit is nothing but it is P1 dash and P2. So P1 dash to P2 we are applying. So this is P1 dash and this is P2. So if you apply, so this is your control qubit 1. So P1 dash is 1. So what it will become? Can anyone tell? Since P1 dash is control is 1, so it will flip the target qubit P2. So it will become 1 1. See here. And now here it is P1 dash is 0. So it will not change this thing. So it will remain same. So this statement, okay, so this part is done. First part is done. Which part is done? Control node part is done here. Now what it is saying is that on the first qubit, you should apply Hadamard gate. Just let me, okay. So Alice is, what Alice is sending is, Alice is sending only one bit of one qubit. This qubit Alice is sending. This qubit P1 dash is Alice sending to Bob. And in this P1 dash, Alice has encoded two bit of information A and B. So understand this thing that Alice is sending only one quantum bit P1 dash to Bob, and she has encoded A and B classical bits information into P1 dash. Bob's side, Bob has applied this control node gate because Bob has both P1 dash and P2 now. So he can apply control node. Control node has been done. Now he is applying Hadamard gate on the first qubit. So see here, this is the first qubit. This is the first qubit. On this, you need to apply Hadamard gate. So what it will become? So if you remember from Hadamard gate's expression, what Hadamard gate does is, Hadamard of 0 is nothing but 0 plus 1 by root 2. And if it is apply on 1, then it will have negative sign. So just on this one we apply, then it will become what? It will become 0 minus 1 by root 2, and it is already 1 here, plus this 0, Hadamard on this 0, it will become what? 0 plus 1 by root 2, and this 1 will remain same. Now we're just multiplying it. So this 0 is multiplied with 1, 1 is multiplied with 1. So just see here, square root 2 we are taking out, so it will become 1 by 2. Is it okay? 1 by 2 is out, and then we are multiplying this 0 with 1, so it will become 0 1. Now we are multiplying this 1 with 1, so it is become minus 1 1. Is it okay? Now we are multiplying this 0 with this 1, so it will become 0 1. Now we are multiplying this 1 with this 1, so it will become 1 1. And see here, minus 1 1 is there, plus 1 1 is there, so they will cancel out. Now it is 2 times 0 1, so it is what? 1 times 2 times of 0 1. So this will cancel out, and this is 0 1 means basically they are A and B. So see here, A and B we are measuring as 0 1. and which is Alice wanted to send 0, 1. So what we are trying to say here is that whatever the inputs A and B are there, if Alice work on this fashion that she applies gates X and Z depending upon the values of A and B, and then Bob does this thing, and this thing is nothing but this entire thing is called Bell basis measurement, and this Bell basis measurement will gives Bob A and B. Is this thing clear to everyone, or any question is there? Participants? Anyone else? If any query is there, then I can tell.
There is one query, probably, I don't know whether it's answered or not. Alice is sending 2-bit information with 1 qubit. Bob is receiving with 2 qubit. I don't know whether it's a question or it's just a comment.
Yeah, it's the thing which is happening. So
Okay.
basically, what they are trying to do in this protocol is Alice wanted to send 2-bit of information, and for that they are using an entangled pair of qubits. No. Bob will not decode before Alice sends. So these are like this only. So first step is that you should have Bell pair. So you create that pair. Then you do the encoding. So that is second part. And this is the third part. You just go there in the diagram here. So this was the first step. First, then this is second step. Third step, she sent this photon. Fourth step, it is done. And at this fourth step end, we get AB here. So actually, Alice is not sending the 2 bits A and B directly. Alice is just sending one quantum bit, and she is encoding this information in this P1 dash, and Bob is able to recover with decoding using Bell basis measurements. So you may say that 2 qubits are used. So that is there because this P2 is already shared with Bob. So in overall protocol, 2 qubits are there, but when we run this protocol, during the runtime, Alice sent the one part of qubit P1 dash only. P2 is already with Bob, and using the decoding thing, Bob will get A and B. So is this thing clear? Any question over there? Then you can ask.
There is a follow-up question. What is the significance of superdense coding?
Yes. So suppose Alice and Bob, there are two parties. Maybe one party, Alice is in India, and other party maybe in America, and they want to send bit information or whatever classical bits they want to send. So there may be a file or some secret things they want to send. So using this protocol, what they can do is with this P1 dash, we are sending only one qubits or photon at runtime, and inside it we are encoding these 2 bits. So only Bob can recover with the help of P2. Without P2, you cannot recover A and B from this P1 dash. So remember, psi state, if a qubit is having an inside state, that is alpha times 0 plus beta times 1. So when you measure this qubit, what you will get? Either 0 or 1. Remember this thing. In superposition, both 0 and 1 are there in quantum thing, but when you measure, you will get either 0 or 1 with certain associated probabilities. And what are those probabilities? For getting 0, the probability is mod alpha square, probability is mod beta square for 1. So actually, from this single qubit, you cannot recover both alpha and beta in a measurement, in single measurement. So as you already have seen that we run this experiment several times, shots, 1,000 times we run, and then we say, okay, 50% time it is occurring, 50% time it is occurring. So with this only P1 dash, any adversary in between cannot get the information about A and B. If somehow adversary has access to P1 dash, but he cannot recover A and B. While at the receiver side, the person Bob can recover with the help of P2 with this decoding mechanism. So that can be a way to think that it can be an application. So one qubit is carrying the information about 2 bits. Secure communication, yes. Yes, Alice chooses A and B. So let's see this protocol, how we can implement it. So this is just derivation. I explained you that how we are ensuring that exactly it will get A and B only. So with this gate operations, encoding and this decoding at Bob part, we tested for 0, 1. Similarly, we can test it for other bit strings 1, 0 or 1, 1. For everything, it will work. That is generalized circuit, and it will work for every bit of every possible bit values for A and B. So in this last part, 1, 1 part, you will get straight minus 1, 1 on measurement here. So the phase will be there, minus sign will be there. But you remember the probabilities are mod square every time. So whatever minus sign is there, that will be plus only. So the exact status is exact status in this case you are getting minus sign, but the minus sign will not make any impact on the outcome measurements. So on measuring this thing, you will get A and B both 1, 1. So no problem. And this is the typical circuit which we can run on Qiskit to test the protocol. Okay, so this part is what? Creating bell pair. So I will just run the code at the end. So before running because this circuit has been created with the Qiskit code. So in the Qiskit code, when we run the code, we get this kind of circuit to implement super dense coding. So there are 2 qubits, and with this we are creating bell pair, and then depending upon the value of A and B. So A and B, if whatever the value is there, if the A and B are 1, then these gates Z and X will be applied. So remember, the ordering is important. You cannot do it in reverse order. So A and B is applied in this fashion, first Z and then X, depending upon the value of A and B. If they are 1, then only these corresponding gates will be applied. Okay, and this part is called encoding. So there can be 4 choices: 0, 0, 0, 1, 1, 0, and 1, 1. So whatever the choice, depending upon the choice, this gate will be applied. Suppose this both the bits are 0, 0, then this gate will not be there. Okay, if both are 1, 1, then this gates will be there. This thing is called, if you remember, it is our decoding part here, but it is nothing but what it is. It is Bell basis measurement. Okay, and what we are promising here is that on measurement we will get A and B at first and second qubit measurement. Okay, so this is the entire circuit working, and in actual scenario what will happen is that Q0 and Q1, so this bell pair will be created initially, and after that this Q0 will go to Alice will have this, and this Q1 will be with Bob. And see this, when this Alice does this encoding, then Alice will send this qubit to Bob. So we call it as a P1 and P2, and this P1 will be modified after encoding, so it will become P1 dash. It will goes to Bob. Bob is already having this P2 on P1 dash and P2. Bob will apply the decoding thing and will get A and B. So is this circuit working clear? Then you have understood the everything well. Participants? Okay. Then just we will yeah, please. Pallivaram, do you have any question? Okay, then we can move to the code demonstration of the super dense coding. So this is the super dense coding circuit which I have implemented. I will share it with you guys. So there are three parts. One part is we call as encoding part. So in encoding, what will happen is, so first we need to create a bell pair. So this instruction will create a bell pair. So I have written comments also. So with the comments help also you can understand the code. So it will create a bell pair and it is created by Hadamard and control X gate. So this part is doing the first thing to create a bell pair between two qubits A and B, or maybe first and second qubit. Oh, so this A and B are the bits we want to send. Okay. Now, depending upon the this value 0010, whatever the value is there, whether to apply X and Z gate during encoding is tested here. So if both the bits are A and B are 00, then there will be here A and B both are 00. So we are sending, so we'll not apply any quantum gates on first qubit. So if both are 1 1, then first Z gate and then X gate will be applied. So this is encoding part, the second part of the protocol. So here what we are doing is, depending upon the values A and B which we want to transfer, we will apply the gates. And decoding side, if you know, it is nothing but Bell basis measurements. So Bell basis measurement, what we do is we apply the control X and then Hadamard, just reverse of the Bell pair creation. So in Bell pair creation, we apply Hadamard and then we do control X. Here the just reverse thing, and then we will measure the qubits. So just we have created this code and just let's run it again, clear all out code and run it again. So the program will ask you, input the bits B and A to send. So this bit value can be 00, whatever you want to send. So suppose I wanted to send 00. Okay. So I just input those values 00 here. Okay. And then just enter. So the circuit will be created. So see here, when the input bit values B, A and B are 00, then during the encoding thing, no X and Z gate will be applied. If you remember from the slide here, X and Z and X gate are applied depending upon the value of A and B. Here in our example, A and B are 00. So A and B are 00. So this gate will not be applied. So see here in the code also, since we are doing it for transferring A is equal to 0, B is equal to 0, so no gate has been applied. And then we are doing the Bell basis measurement. So what we should get at the end, we should get 00. So see here, we run the circuit, only we are running it one time. So see here, we are getting state 00 one time. It means we wanted to send 00 and we are able to retrieve 00 at the end of the measurement. Let's test it again for another input. So that input can be 1 1. Suppose 1 1 is my input. I wanted to send A is equal to 1, B is equal to 1. So just I input that term and then we will the circuit. So since A and B both are 1, so Z and X gate are applied. Okay. And now we want to see the results. So we are running the circuit one time and we are getting the state 1 1 on measurement. See here, you're able to see 1 1 at the mouse pointer 1 1 we are getting one time. So basically this is the information Alice wanted to send and Bob is receiving the same. So I think I am done with the super dense coding this thing on Qiskit, and we have understood the protocol also. Just to recap or summarize, this slide will summarize the thing. So in teleportation, what we were trying to do is we wanted to transmit one qubit of one quantum bit using two classical bits. So in both the protocol, a resource, Bell pair resource is used. Bell pair paired between Alice and Bob. So it is already there. So it is a prerequisite kind of thing. Prerequisite. So what is the prerequisite here? A Bell pair created and already shared between A and B. So Alice and Bob have one part of the entangled pair with them. And then what is the difference? So this thing is applicable for both. A bell pair is created and one part of the qubit is given to Alice and other part is given to Bob. Now in teleportation, we wanted to send one qubit using two classical bits of information. So remember in teleportation, if you remember, then Alice shares these two bits of M1 and M2 on her measurement. So what Alice does? Alice also does the Bell basis measurement and tells the information M1 and M2, these two classical bits, to Bob. Okay. And then Bob is able to recover the state qubit psi at his side. So in this protocol teleportation, two bit of informations are sent to have to transmit one qubit, while it is the exactly opposite in super dense coding. We wanted to transmit two classical bits using one qubit. Okay, so we send this p1 dash qubits and we are able to recover two bits of information at the Bob side. Just remember this thing. So basically this qubit is being sent and A and B are recovered. So just a bit of you can say that they are almost similar, but the purpose is different. In first case, you wanted to send a quantum bit. In second case, you wanted to send two classical bits in a qubit. So I have covered everything which I wanted to cover as per the charter. Any question is there? Then I can talk questions.
There is one question which was posted, which is here we are sending classical data by quantum means.
Yes. So in a single qubit, we are encoding two bit of information, and that we are able to reconstruct or retrieve at Bob side. Maybe if one of the student can rephrase for everything, then it will be. So you could recap teleportation again. It is confusing after learning super dense coding. Okay, so let's go to the super dense teleportation part here. Just remember here, in the teleportation, what was our goal? Our goal was that Alice is having a qubit psi. She wanted to send this qubit to Bob, and they already have this two qubits by entangled pair with them. The qubit 2 is with Alice and qubit 3 is with Bob. This qubit 3 is with Bob. Alice do this Bell basis measurement at her side and share this two bit of information. So what she wanted to do is she wanted to send a qubit psi with the help of two classical bits M1 and M2. And it is done in the teleportation. So basically in teleportation, we are trying to send a qubit state psi with help of two classical bits. While in super dense coding, we wanted to send two bit of information in a qubit. By sending one qubit, we want to transfer two bits of information. Just see here, this two bit of information is encoded in one qubit, P1 dash. I hope it is clear now. So if there is no question, then we can stop here. And if you have further any query or any doubt, so then you can write my email address, that is harish.sahu@gmail.com. harish.sahu@gmail.com.
All right.
Uh,
So thank you very much, Dr. Harish Rao, for taking time and giving us these four sessions related to quantum communication. And I hope, as the messages are showing, the participants have also gained a lot from you, and they have been interacting with you with the various questions which you have patiently answered. So thank you for that also. So if you have any questions, participants, if you have any questions, he has already shared you his email. You can reach out to him for any things which I mean still are not clear. Probably, uh, I mean those things can be answered through the email from him. So we
Okay.
end this session, and tomorrow we'll be again meeting at 3 p.m. with another session by another speaker. So thank you very much. Thank you all.
Okay. Thank you, Professor Mitharwal,
Thank you.
and thank you, participants, for patiently listening and participating. Thank you.